do that.
Oh, it's killing me. My wife is in Mexico right now, and she just started trying to video chat me. Let me close off Skype so I don't break the internet doing two video conferences at once.
The wonders of the internet.
Yeah.
All right. Cool. Here we go with Rob Sherwood from Big Switch Networks, inventor of FlowVisor, and now a big proponent of bare metal switching. And I guess we're going to talk about both of these things today. So thanks, Rob.
Thanks for having me.
Cool. So just maybe we'll start talking about FlowVisor. Actually, it's a very opportune time to talk about it. This particular week, the students are going to be implementing a poor man's version of it in POX, I guess you could say. So it's great to be able to ask you some questions about it. I guess just motivation. First of all, what caused you to kind of recognize that there was a need for something like FlowVisor? Like, were people talking about needing to slice networks?
No.
Where did the idea come from?
The idea comes directly from a hypervisor, which is you have one set of hardware, and you want multiple people to use it. I feel like it's actually better motivated than actually even a server hypervisor, just because putting together the hardware for a network is expensive, and it's very hard to give each grad student their own network, right? You can probably, if you have enough money, you can give each grad student their own server. Virtualization makes that easier, but you can't give each grad student their own network. And we were trying to run this, in the Gates building at Stanford, and we really wanted we wanted each grad student to have their own play space to work on something. It was very clear we weren't going to get multiple networks, and even more so coming out of my dissertation work where I was doing topology discovery, I was kind of militantly bent on the idea that you can't have a simulated topology that nobody really knows what the topology of the internet is, and so you're actually better off using the actual network. And that was kind of how that all came together.
I guess like the title of your paper, like, can the production network be the testbed? Or
yeah, exactly.
It's really the motivation. Actually, did that ultimately come? I mean, did that come to fruition in some sense? Like, you were able to actually play on the production network, thanks to FlowVisor?
It was what I jokingly call the lowercase p production network. So lowercase p is, if it goes crashing down, then people get annoyed and people get mad, but no one gets fired. That's much more the case on like a typical campus network. And practically, at Stanford, the network that I used to check my email, like the everyday network, was FlowVisored. Unfortunately, it's become a verb now, but yeah. So that everyday network that I use, so everyone in Nick McEwen's group, who I was working with at Stanford, all of their network went over devices that were controlled by FlowVisor, and it was actually running all sorts of graduate student experiments in parallel in different slices. And we spent the better part of 2 years debugging it, but eventually got fairly stable.
Very cool. I guess and are the people who are using it now, are they the same sets of people? Like, I assume it's still running at Stanford, for example, but are there other sort of groups of customers, I guess you might say, or is it still kind of like
yes.
test?
Although I have to admit, I haven't really been in the thick of it for a couple of years now. The Open Networking Lab folks, Guru Parukar and Ali Shababa and company have taken that over. To best of my knowledge, there's kind of a bunch of Genie folks who are using this. So actually, I'm still on the mailing list for that, where they announced downtime. It's actually like an official kind of production service for them. There's the Ophelia group in Europe, they're using it. And there's actually kind of a long tail of people using FlowVisor in weird places. Like, there was a guy in an ISP in New Zealand who was telling me he had FlowVisor deployed, and when was it going to update it for 1.3 and that type of thing. So it's gone surprisingly far. I also pretty surprised at how people use FlowVisor. So I never really thought about the power of having an API which is the same down-facing as up. And one of the things that kind of falls out of that I never even thought people even thought about as a use case, but people just started doing it, was actually recursive FlowVisors. So having like a base FlowVisor, and then in a slice you have another FlowVisor, and that further subdivides just that slice. And I thought I honestly, if you had ever asked me if the code I'd written would work for this case, I would have said probably not. But the first bug report I got was about a guy running this apparently 3 levels deep. So there's like a base FlowVisor, and then a slice was another FlowVisor, and a slice was another FlowVisor after that. And what he told me was he actually wasn't doing anything terribly intricate in the flow space. It was actually that he was using FlowVisor almost as a monitoring tool for, is the controller up? How many flows has it pushed down? Tell me things about the controller that are independent of the actual implementation.
Hmm. And the additional layers was buying him what exactly? I mean, why would you need
additional levels of visibility?
Interesting. Okay. Yeah, I guess that was another thing that I imagine that there would be these strange use cases, or at least unexpected use cases for FlowVisor. Were there others? I mean, besides the testbed application, are there other ways that people have used it that you find interesting?
There's the network monitoring case. There's actually this other interesting case of, so it's what my co-author KK Yap used to call horizontal slicing as opposed to vertical. So if you imagine, kind of the OSI model, in what I would call a vertical slice, you're required to implement the L2 forwarding, the L3 forwarding, maybe some ARP agents on top, maybe some DHCP on top. You actually have your whole network. And then, but depending on how you want to cut the flow space, maybe you actually can separate out the L3 and below from the L4 and above. And so maybe you don't want to handle ARP, maybe you don't want to handle DHCP, maybe you just want to handle kind of specific layer 4 ports and how the layer 2 forwarding works for them. And so that's another way that you can actually slice the network. And he called it horizontal slicing, kind of like across the OSI layer as opposed to like up and down, creating parallel OSI stacks.
Interesting. Yeah, it seems like like a theme that's coming out is like the sort of visibility or lack thereof that FlowVisor can give you allows you to kind of like roll your own abstractions and
yeah. I mean, the other one that floored me, folks at Internet 2 came back saying they were having performance issues with FlowVisor, and it had been running pretty well for a couple years, and I was a little surprised about it. They had such a complicated flow space that it was on the order of 60,000 flow rules. And apparently the problem was, and it was never written for this, it actually kept going because internally it kept views of things, so it was fairly efficient kind of in FlowVisor's fast path, even though it's on the control path. But every time you updated a rule, it would actually write the entire config from scratch down to the disk, which made sense when you think of the config being a couple hundred lines, because that's what we had it played with. And so, the newer versions of FlowVisor actually use kind of an ACID-style database where it performs updates on the rules incrementally as opposed to all at once.
Mm-hmm.
I don't know, it's a very fun experience.
Wow, cool.
I'm trying to explain this to grad students of having a piece of code that you actually support and get users for brings out all sorts of different aspects of the research rather than the one-shot use case that you had in mind. And it's something that I highly recommend to people if they ever get a chance.
Yeah, no, that's interesting, actually. I mean, I think it's fitting that we also talk with Larry because, he wrote a paper on this whole, I think he called it like, experience-driven systems research that kind of exactly describes what you just said, which is that the process of deploying something actually opens up all these these unexpected directions that were not where you started.
Well, and practically it gets people closer to the real problems that operators are having rather than kind of the interesting problems that are fun to whiteboard. And I kind of a personal soapbox of mine is trying to get the researcher communities and kind of the engineering operator communities closer together. And so this is one avenue of doing that.
Yeah, fantastic. No, I think that seems to be like a perpetual struggle, I guess, in the networking area.
Yes.
And we continue to see it in the SDN space as well. I guess along those lines too, like you're talking about kind of the evolution of FlowVisor. Do you see it how do you see it evolving in the future? I mean, it seems like there are there may be other needs coming down the road, like this whole. Do you see different abstractions? Do you see like completely different use cases coming?
So There's a couple different directions that the folks at ON Lab are taking it. One is, so what FlowVisor provides is flow space virtualization, but not really topology virtualization. So it provides, let me go on a small tangent of virtualization versus slicing. So in virtualization, you are given a slice of the pie in practice, is my thinking, but you aren't told that you're given a slice of the pie. You're given an abstraction of a pie.
Right, right.
And then in slicing, you know exactly that you've been given a slice of the pie, and you know what the borders of your pie are. And if you try to eat outside of that, then you kind of know that you're on your own. And so FlowVisor doesn't do topology virtualization, meaning that it won't make up a switch that doesn't exist. It won't make up a link that doesn't exist. But you can ask it for a subset of the network. So yes, include that switch. No, don't include that link. What the folks with ON Lab are doing with the next generation of FlowVisor that they're calling Open Vertex? No. I'll have to look up the name. It's not open source yet, but is actually the full-on topology virtualization. And so that is interesting for a researcher if they want a more complex network than what the underlying hardware allows them to do. Apropos of my kind of earlier internet topology discovery research, I think it's a little bit of a red herring, just because people tend to make up topologies that seem like they're a good idea, but don't actually reflect the realistic topology, and so that's why I was always more on the other side. Mm-hmm. But it's a good idea, and we'll see how that works. The much harder problem, which there aren't as clean solutions for, but I continue to think about them, is how to virtualize in the multi-table case. So one of the ways that FlowVisor works right now is you can actually have a one-shot stateless decision for, is this flow rule allowed or not? Because if you're writing to a table, there's all the packet processing, a single table design, all the packet processing happens to that one table at one shot. And it's easier for those FlowVisor to be roughly stateless to figure out, should I allow this rule or not, or do I need to modify it? In the multi-table case, when you write to a rule in the fifth table, whether you're allowed to do that or not depends on what you've done in the first through fourth table up to that. And so if those packets arrive either out of order, or if the above controller programming down sends it out in a different order, it's actually very difficult to understand from just a policy perspective, should I allow this flow or this rule change or not? And so what ends up happening in production networks with, say, virtual routing and forwarding, VRF, which is a well-known virtualization primitive, is you end up qualifying everything on some sort of global label, so an MPLS tag or a VLAN tag or a VRF tag or something like that, which is to say, you can do anything you want in this space as long as it's qualified by this label. And so I kind of imagine that's where FlowVisor will go in the future as people move it to multi-table designs. Although practically speaking, that's no longer my day job. So if anybody's interested in doing that work, let me know. I've got some ideas. Oh, I think I may have lost you, Nick. All right. Assuming you can't see me, I'm going to grab some water. I'll be right back.
Oh, we're back.
All right. Excellent.
No idea what happened there.
It's okay.
We got horizontally sliced or something.
All right. So where were we?
That was we were. Oh, so I was just about to ask you. You uh, you had mentioned basically these use of tags as a way of dealing with multiple tables,
Mm-hmm.
and that actually was another question I wanted to ask, because you mentioned sort of like the way that it's done with other types of protocols is by using tags, and another question I wanted to ask about that was um, whether there were, I mean, do FlowVisor concepts apply to other things that are not OpenFlow? Like, I mean, certainly they do, but do you know? Are you aware of anyone who's kind of using FlowVisor or a variant of it, or a FlowVisor concepts with
Uh,
different sound?
so just so that no one ever thinks that they're cool or that they've done something new before, I was actually talking with Vince Cerf about FlowVisor back in the early days of SDN. He says, "Oh yeah, we did this in the early days of the ARPANET about 30 years ago." So uh, I guess the short story is that people have been playing these types of monkey in the middle type tricks forever. I mean, you can think of at some level this is what NAT does. This is what my TCP sidecar work did in the TCP space. This is what long before there was the VX instructions on the VT instructions on the Intel chips. This is what the VMware folks had to do in the x86 instruction level. Anytime that you are doing the protocol in or the API in is the same as the API out, um, there's kind of a certain set of things that you're like, okay, well, I'm trying to do isolation in this space. I'm trying to really hack my way through the protocol to provide the same virtualized feel up as you are down. I mean, you see this even in RAID, right? I feel like this same paradigm is repeated through many parts of computer science.
What about the types of isolation and things that FlowVisor doesn't do? I mean, it's I think you mentioned before it doesn't do topology virtualization. But are there other things that like it doesn't do that you think it should do? I mean, it seems to me that it's pretty focused or sort of operates on slicing on flow space primarily. But are there other things that you would like to see it do?
So there are a bunch of things, and we actually even get into this in the paper of what it should be doing versus what it does do. So there's a control channel between the switch and the controller, and performing isolation and effectively bandwidth protection between that channel is actually kind of like a well-known hard problem, even without virtualization. So if you look like at a standard router, trying to ensure that the BGP announcement messages that arrives in the front panel line card get correctly punted up to the control plane supervisor module, and that they don't compete with the LDP packets and there might be some sort of ARP storm or DCP storm going up to there. And you're trying to make sure that those things don't saturate that bus is kind of a well-known hard problem, but it has functional solutions, but it doesn't have great kind of closed form solutions, which is to say, you insert a whole bunch of rate limiters, and you kind of know that the sum of the bandwidth you're reserving is over-provisioned. So if everything goes badly at once, then the box is just going to die, or the system's going to die. Right now, at least with OpenFlow 1.0, there was not enough of those knobs exposed, even though they exist in the underlying hardware, to really make sure that's isolated properly. So if you have two badly written reactive controllers running in parallel, their performance is going to be bad. That's definitely one of them. Another one, which is a hard thing to do, for the underlying forwarding memory, everybody talks about TCAM as kind of the memory of choice, and it's certainly the most flexible one. And what's nice about TCAM is it's logically like an array of wildcards. And so how do you partition up an array of wildcards between n slices? Okay, that's kind of easy. You could chop them up into n ways, or you could do some sort of optimistic locking or something like that. But there are other memories that don't have that nice structure. So like a CAM or any sort of hash-based memory, that's much harder to provide hard isolation for. So you imagine, if you've hashed into 7 of the 8 available buckets, should I have stopped you, right? And so those are things that I think at least with the current forwarding ASICs and the forwarding memory, it's going to be hard to provide real like bulletproof isolation the way you would get on a hypervisor, like a server hypervisor.
Mhm. Yeah, and I guess yeah, it seems like there are other cases too where you might have overlapping controllers, but like if one of them is like only needing to read and not write, you could maybe there are cases where maybe you can get away with some overlap in
Yeah,
the
and
flow
I don't
space.
know how well publicized it is, but even the FlowVisor code actually has a read-only notion of a flow space and a write notion, and so those are separate bits, almost like on a file system. And so we actually had that for monitoring purposes, even back in the Stanford Gates days.
Ah, cool. Yeah, so
Um,
it seems like there may be other cases like that where you could allow sort of certain types of concurrent.
well,
Uh,
and there was an interesting one that we did with our wireless work, which was asymmetric flow space. So the path from A to B belonged to one slice, and from B to A belonged to the other. And so the idea was, in a wireless network, you should be able to control all of the packets coming to you. And so the idea was everything going to you, you could decide, do you want it? What path does it take? And the kind of the pitch was your mobility agent can communicate with the network and help better figure out how to get packets to you when you want them. But as soon as you put a packet on the network going to someone else, it's no longer in your control.
I see. Yeah, that brings up just like broader issues too about authorization and things like that, right? I mean, it seems like, I mean, have you thought about sort of expanding the notion of ownership of flow spaces beyond just sort of like, oh, I own this part, but maybe like I'm authorized to do something on this part of flow space?
So yes, and actually, so with my current work at Big Switch, people ask me often, so are you using like FlowVisor technology underneath? And the answer is not at all. So FlowVisor is very nice if you have these very hard silos of, slice A is not going to touch slice B. But we actually have exactly the opposite thing, where we almost want intra-slice modularity, where I want to reuse code there. I'll only have one slice because there's only one thing this part of the network's doing. But in there, I'll have almost kind of like controller A that takes the first pass at things, and it might do nothing, or it might decide to do something, but then controller B might logically override that, or it might augment it, or it might do its own thing on top. And trying to
Kind of
get
like one controller subsumes the operations of another.
yeah, and so one audits or one supplements, but it's certainly not this hard isolation between them.
Yeah, interesting. That seems like one interesting case. The other one I was thinking about too is like things like extranets, right, where you have maybe two different networks or two different control parts that you want to basically, these two shouldn't be able to talk to one another, but they should both be able to talk to something in the middle. But you don't want, transitive properties to start.
Yeah. Well, and so what's interesting, and this throws people for a loop a little bit, the entire idea of a FlowVisor is very much for hardware owned by one kind of administrative entity, like kind of at an AS level. And so it doesn't really make sense in my mind to have a FlowVisor that spans ASs. So effectively, the FlowVisor it has like super user access to each of the switches it controls, and then provides kind of a single user, a multi-user experience to controllers on top. But it's not multi-user in a sense of multi-administrative domain. And so, what is the protocol that FlowVisors in different administrative domains talk to each other to make sure there's end-to-end flow space? And this is some of the work we got into with Genie. And you're reserving kind of end-to-end flow space across a multi-administrative domain network.
Is there a solution to that yet, or?
I mean, I know that Genie people are doing it. Just along the networking dimension of that problem, I think it's effectively solvable. What's the sleight of hand trick that FlowVisor does is it actually describes the policy language using flow space, which is the same language that the FlowMod OpenFlow uses. So doing things like a mask, like policy says you can do X, you have tried to do Y, what is the intersection of this, is actually almost the same operation of a packet lookup of what what role applies here. And so it's something that is a bit subtle and maybe is obvious in retrospect, but we actually got wrong a couple times beforehand.
Interesting. What about security concerns? I mean, it seems like sort of almost by its nature, FlowVisor tries to provide some level of, you might call it security, through isolation. But are there security do you think there's sort of open security issues either in terms of things that FlowVisor itself might be vulnerable to, or security applications that you might implement with FlowVisor or an extension of FlowVisor?
So security applications, definitely. Let me go on a little bit of tangent about why there are no new security implications with FlowVisor, like just by having the control. Cool. So if you think about like a modern multi-line card chassis-based system, so if you're familiar with the model numbers of stuff like Cisco's CATS 3000, Nexus 7K, Juniper's MX, things like that. Basically, what you have is you have a whole bunch of line cards. And then you have kind of a supervisor module or a route engine, which is basically a PC. And that PC runs user space processes, and those processes communicate information over an internal backplane down to the line cards. And the protocol of that communication is very proprietary. It's very closed. I actually joke that that's closed flow. And so that notion actually helps people better understand what OpenFlow is trying to do. Right? It's not trying to act like a routing protocol between these modules. It's really trying to extend and be the same architectural thing as closed flow. That is the logical programming protocol from the supervisor module down to the line cards and to the fabric backplane. And so from that sense, people are like, well, isn't a centralized control plane inherently less secure? Well, no, I mean, it puts a lot of eggs in one basket, but you already have that one basket with your supervisor module. And that's why you have lots of best practices of you don't put the IPs of your supervisor module on a publicly accessible network, use two-factor authentication getting on there, you restrict by IPs even in that case, and there's a bunch of things that you do because, yes, it's a high-value target, and FlowVisor is a high-value target. But there's a whole bunch of standard things that people know to do to secure them because it's the same problem that they have today. Now, that said, to your question about are there interesting security applications that get enabled, definitely. So even at Stanford, this is where the read-only flow space comes. We had a slice which spanned the other slices and could monitor the sum of what was going on in the network. In fact, if you look at some of the FlowVisor videos, you get this kind of like 6-panel view of 6 different slices, and the center middle topology was the overlapping one that showed you the sum of all the flows. Right. And having that super user view, but in a read-only way, well, I actually thought that was pretty cool.
That's pretty neat. So that's sort of a monitoring application, I guess you might say.
Exactly.
I see.
And then folks from openflowsec.org did a couple of interesting things. So they had their Fort Knox, and eventually they ported that work to Floodlight. It was called SE Floodlight. They had kind of the next phase of that, which is a FlowVisor type application, which would actually enforce other forwarding paradigms. Maybe something more complex than a flow space style isolation for trying to say, are you allowed to make this flow entry or not? And so like having this policy point in the middle between the underlying switch forwarding hardware and your control application, it's a fairly powerful tool.
Yeah, I mean, it seems to me like you could use it, to implement all kinds of different separation. I mean, as you mentioned, sort of, separating different parts of the topology, but also separating controllers from one another. Or not, as the case may be, as you already pointed out. So, yeah, it seems like a pretty useful primitive for doing that, for enforcing that kind of isolation of separation. Cool. So I guess you have a day job as well now, as you alluded to, which does not involve FlowVisor full time. Like you've been giving some talks and things on something called bare metal switching, and actually I think the next week of the course after virtualization, people will be looking at all this programmable data plane stuff that basically didn't exist a year ago, and now it's kind of all the rage. But
Yeah.
What's bare metal switching? Like, what's that about, and why should we care? Like, why should people doing SDN care about bare metal switching?
So let me answer it in a little bit of a roundabout way. It has a short answer, but I'm going to indulge myself. 2008, 2007, OpenFlow, the entire purpose of this was effectively as a bad engineering compromise, which is to say, everybody who wanted to program networks wanted to program the lowest level of the forwarding chip, with no software in between. Like, this is, Linus Torvalds, back when men were men and wrote their own device drivers. Like, that's what people wanted. But the reality of the business world was that, the large incumbent vendors were not going to let you just throw away all of their software that they had spent, tens of years working on. And so, kind of a compromise was to expose a higher level remote API, which eventually became OpenFlow, to do some of that programming. And so OpenFlow pushed forward as, this is kind of a compromise where we're not going to let you put we're not going to let you put new software on the box, but we'll give you some hooks to do some interesting things. And so flash forward, what bare metal switching is you can actually buy just the bare metal, that is no software, and put all the software on it yourself. And so it's like that next step past writing a controller is you now have to write an operating system for the switch as well. And what's interesting is once you have that, actually the value of OpenFlow as an architectural piece becomes reduced because now it's just an RPC language. And whether you're communicating the flow information over OpenFlow or if you want to put it into Thrift or Google Protocol buffers or JSON RPC, it doesn't really matter. You're communicating.
Right. You're starting from zero, so you can define what that control protocol is. You're not
exactly
bound by whatever software the switch ships with.
And more to the point, folks who make those chips are actually becoming more and more aggressive in terms of making the lower level hardware details available. So, like, I'm under NDA with all of the chip makers: Broadcom, Intel, Marvell, these people, Mellanox. And they give me the lowest level hardware information so that I can actually build up the complete software stack.
What caused the shift? I mean, you mentioned, like, initially when OpenFlow was kicking off, there was some pushback against doing this, but now that's the tide has turned. So what caused that to happen?
So a whole bunch of things came together at once. One is hyperscale networking. So just the Googles and Facebooks of the world just started buying so many boxes that the number of nodes being sold changed the commodity of scales of the economics of things. And so now it was actually possible to have third parties building all of these different components to make a big solution, right? So if you look at every network vendor in the world right now sells a chip, a switch based off of Broadcom silicon, with a box built by somebody else, and has software in it that might be written by them, but probably has some stuff from other third parties. And so this whole space, because there's become so much money in it, has horizontalized and has become kind of this component ecosystem. So that's the kind of the hyperscale networking aspect. At the same time, Cisco did this thing, and I absolutely understand why they did it, but it'd be interesting to see when all is said and done if it was a good idea or not. They actually produced a product that competed with all of their partners. So the UCS product was a combined server network storage, where it used to be that HP, Dell, and IBM were the number 1, 2, and 3 Cisco resellers because they would sell the servers and Cisco would sell the network. And as soon as Cisco started competing with them, what happened is HP bought 3Com, IBM bought Blade Networks, and Dell bought Force 10. And now they all turned into competitors. And so those competitors were looking for what is the number one thing we can differentiate from our customers. And they talked to their customers, and they all said, we feel like we are trapped and locked into Cisco. Oh, I think I lost you again. Let me know when you're back. Are you back?
Yeah.
All right.
Yeah. So you were saying that the vendors started competing with one another.
Yeah, and they were all looking for a way to differentiate themselves from Cisco. And they talked to all the customers, and they all said that the number one thing that we're unhappy with is vendor lock-in. We want the system to be more open. And the last thing that happened was the companies who had been supplying the boxes and the underlying silicon to these, to the Junipers and the Ciscos and Brocades of the world, made the tipping point to decide to sell these boxes directly. They're saying, we're getting, lower margins. Cisco gets like 70, 80% margins on selling a box. They're selling them at like 20, 30% margin. This doesn't seem right. Let's go direct. And the Facebooks and the Googles and the Amazons of the world have been doing this for a while, but something happened at the beginning of last year, and I haven't quite figured out what, but enough people started talking about, isn't this actually a commoditized market? And then all of a sudden this huge groundswell of things started changing. It was very fascinating to watch. And so right now you can buy, favorite website of mine is whiteboxswitch.com. You go to the website, you pick the switch you want, you see what the price is, you click a button, you insert your credit card, and you get a switch. And then on it, it comes with a piece of software called Oni, which is basically a open source bootloader, and it will let you put the operating system, the switch operating system of your choice on there. And so, actually, I don't even know if you've heard about this. We should chat more often. We now have an open source project called Open Network Linux, which is a base operating system you could put on that switch, so that you as a grad student or DIY professor type, you don't have to write your own fan drivers. You don't have to write your own SFP modules. I have learned so much about the hardware internals of switches that no one ever really needs to know. And we solve a lot of those problems for you, so that if you wanted to write your own protocol that was OpenFlow++, you don't have to deal with all the rest of those problems.
That sounds like a huge win for getting bootstrapped really quickly.
Yes, that's certainly the intent. And actually, it's the underlying part of the operating system that we put on the switches commercially. So we're trying to support it and make sure it's useful for people. So that's opennetlinux.org if folks are interested.
Yeah, I'll definitely check that out. What are the implications for switch vendors? I mean, it seems like scary times or maybe huge opportunities depending on who you are, right? As you describe it, the whole thing just broke apart, right? You've got people selling components.
I think the reality is the pricing models for these things have been broken for a long time. If you look at what the costs are predominantly on the software side, and people have been selling a vertically integrated solution. And so now as people start to see, okay, well the hardware is actually really cheap and it's the software that I'm paying for, it will take some changing of people's mindsets. And frankly, you can't have a $50+ billion industry at 70% margins for too long. Eventually, that's going to start going down. But I think that a lot of the incumbents have good quality software that people are still willing to pay for, and it's just a matter of what I'm hoping to see, and I'm hearing rumors that it will happen, that big name people will actually start selling their software stacks independent from their hardware. And so you actually saw, I don't know if you saw, but Dell made a big announcement about this recently. They're the first to take that plunge. So if you buy a switch from Dell, you get Oni, this bootloader on it. And then you can put the software from Dell from their Force 10 acquisition, or you could put the software from Cumulus Networks, which is another startup, or you could put the software from my company, Big Switch Networks. And there are more people filling into this space, or you can put the open source Open Network Linux that I was talking about. And you can actually dual boot your network, which is just a fantastic thought.
That's amazing.
So
that's how is it going to change the game for OpenFlow? I mean, you mentioned before kind of OpenFlow being this compromise, if you will, and maybe if you had to if you hadn't found yourself in that environment, you might have designed people might have designed the that control protocol differently. But now we are there, right? So what would you? I mean, is it going to be OpenFlow, or is OpenFlow going to be you know, is this the end of the line for OpenFlow, and we're going to see something totally new as a control channel there? Or?
So we'll have to see. We spent a lot of time internally building up OpenFlow tools, and so we have this tool Loxy, which will, given a high-level description of OpenFlow, produce the Java bindings for it, the C bindings for it, the Python bindings, the Wireshark dissector, and like that type of stuff is useful.
Yeah, I gave that a little bit of airtime in the course. Actually, I spoke about it briefly. So.
And at its heart, OpenFlow is basically a TLV-based language that's fairly extensible. And we've actually been able to continue to use OpenFlow for even our commercial products, with some extensions on top. But through the standard extension mechanisms, they're all kind of valid extensions, if you will. And so from that standpoint, it's actually been, it still continues to have legs. On their end, this is part of what I talk about fairly often professionally, so figure me if it sounds like a soapbox. The OpenFlow go-to-market model, which is the way that you, the customer, might build a network, has, in my mind, been fairly broken. And so the idea that you would buy a switch that had OpenFlow software all on it already, and you'd buy that from company A, and you'd buy a controller from company B and an application from company C, and these things would all kind of magically work together, I don't know that that will ever happen. And so what we have is and this is, I'm espousing this, both with my commercial hat on and not. We have a model where you buy the controller and the application from us, and then the switch will actually net boot the operating system from the controller. So you're actually getting the hardware from a completely different company. It has no software on it. That's the bare metal vision. And then you get all the software from one company. And then there, at least, you're guaranteed that the thing will work. There's open APIs into the top of the solution, but into the intermediary parts, that is, from the switch to the controller and from the controller to the application, it's not, at least right now, a user-facing thing.
Right. So there's almost there's no need to interoperate at the moment.
Exactly. Yeah. And but note, and this is maybe a bit of a subtle, but it's a critical point. There's no vendor lock-in between the hardware and the software. So if you decide that the software you get from company A is crap, you can put the software from company B on it. Or if you decide software from company A is great, but you want the next generation of hardware, as long as that's on the qualified list, you can do that. And so you actually have decoupling there. Other people are calling it the disaggregation model.
Yeah, I guess that will keep both parties on their toes, as you've alluded to, right?
Yeah. Well, and also it's something that I take as a truism that people could argue with or not, but I think in the history of tech there's great hardware companies and there's great software companies, but there's extremely rarely a great company that does both hardware and software.
Yes.
So, they're just fundamentally different mindsets, and it's very hard to build up the expertise to do both.
Yeah, absolutely. So what do you think? We talked about, at least in our discussion, you brought up a few interesting kind of open problems on with respect to FlowVisor, but with regards to bare metal switching, this is something we're just starting to hear about now. Like when I do this course in a year, or as students start to think about, like grad students start to think about things to work on, do you think that there are interesting problems to pay attention to now?
So I will pitch to you the hardest problem that I know of that I have decided not to bother solving. And then you can take it as you will, whether it should be solved or not. And then independently, if you think it has a solution. So a compiler has a relatively straightforward job in which to say, if I'm trying to add two numbers together, the compiler doesn't have to decide, okay, does this Turing complete chip support addition? Like, it always supports addition. And then it's just a register scheduling problem. It's a memory, when do I load when I do the loads and stores and that type of thing, right? The question is, can you build a compiler for ASICs? And this is a completely different problem, because then you have to solve the problem of, if I were to do something as simple as addition, maybe ASIC A supports it and ASIC B doesn't. And inherent to being an ASIC, if it doesn't support a given operation, ASICs are not Turing complete. You can't emulate it in hardware. You can't fake it somehow. Either it goes in the register that's dedicated for that purpose, or it just won't do it.
Or it chokes, basically.
Yeah. And so OpenFlow at a high level, it was trying to present this kind of unified abstraction of decouple like abstract away the hardware as well as decouple the data plane from the control plane. And what I'm finding is that it is basically technically infeasible to build a single OpenFlow agent that is all things to all possible applications. Because exactly you can't generalize things that are so specific as an ASIC.
Yeah.
And maintain wire speed.
Some might claim that at the ASIC level, like the set of operations that you need is limited enough that you might be able to sort of you might not have to deal with unknowns, I guess, because there's just a relatively limited instruction set that could ever exist there. But I don't know if that's true or not.
What's interesting is between vendors and even within vendors and different chips in the same product family, you have vastly different ways that the hardware is laid out. And so things that are possible in one are not possible in others, or if they are possible, you have to do it a completely different way. It's very much like assembly programming.
Right.
What we're finding is take all the chips from one vendor in one product family, right? So this is chips made by the same people for roughly the same purpose. There's actually even then still lots and lots of differences. So these companies will actually produce their own SDKs, which are the best guess of the abstraction model from the people who designed the chips for this purpose. And even then we're finding that we have to bypass this abstraction, like not a lot, but certainly not infrequently. So even the best abstraction created by the people who made the chips, is still imperfect. And so to claim that you could do better than that across product families, across chip vendors, it's just a problem that I don't think has a good solution now. And certainly from a commercial perspective, I've stopped trying to solve that problem. What we do right now is we have OpenFlow agents where we send an application message down that says reconfigure yourself for this application. And what it means to configure yourself for that application is something that is just completely not at all standard and basically can't be standard. And I don't know of a better way to solve that problem.
It may just be that you're going to have something specialized for ASIC, or at least for families or something.
And in general, the people think of this as a horrible thing, and I actually don't think it is, right? I mean, even at the highest level of our applications, we need to understand what this information is, and software has all sorts of different levels of abstraction, and trying to standardize software layers is an inherently difficult and messy and frankly unproductive thing to do. And so exposing the low-level hardware and letting people figure it out for their application what is the right abstraction, I think makes a lot more sense.
Yeah. Cool. I guess we'll wait and see. Like maybe this time next year we'll have more answers.
Yeah. Well, and certainly this time next year we'll have the thing that I'm most excited about is more and more chip vendors are starting to publish not the low-level hardware details, but actually open APIs into like a closed-source SDK. And so people are getting more and more familiar with what the actual hardware limitations are, and that's forcing a more productive conversation. Another thing that I would point you to is Broadcom's OFDPA. It's a binary SDK on top of some of their chips that you can actually. The source code for the SDK is not open, but the API is, so you can at least see what's possible.
Cool. Interesting.
Or at least a subset of what's possible. And I can send you these links.
Excellent. Yeah, no, it'd be good to get the pointers. I'd definitely be interested in seeing those. Well, awesome. I guess we've probably taken up enough of your time for one day, but this was fun. So we should definitely do it again sometime, especially with the speed at which these things are going.
Yeah, definitely.
Talk about. So cool. Thanks.
All right. Well, it was great chatting with you, and thanks for having me.
Thanks a lot.